last section, we discussed the equilibrium constant K, Kc. We touched on the fact that we get different Ks for different specific kinds of reactions. We spoke about Ka, which is a dissociate or an equilibrium constant for an acid. Now, in this section here, we're going to continue with our equilibrium constant. Okay, and we're going to look at two others, water and solubility. This one actually is very interesting one, the solubility one. We'll get to him. Let's first of all look at water. Okay, now water itself dissolves in itself. Now you're probably looking at this video and you've probably stopped it right now and said, yeah, right. But it does. Water actually contains ions inside itself. It splits. All right. Water, H2O, like that, all right, as a liquid, can exist in equilibrium with, well, first of all, this can split into an H plus and an OH minus. Remember we had this inorganic. We formed alcohols with that, didn't we? Right? We used that to form water when the hydrogen went. Remember? We used the H plus, the OH went and formed an alcohol, the H plus linked to a chlorine or whatever, okay, when we had a haloalkane. Now, thus water can exist as an H plus. And what do we know about this sad little guy called H plus as a proton? Well, I always say he's unstable. Okay. We've seen him in dative covalent bonding. Oops. Dative covalent. Dative covalent bond. It's unstable. He goes and he finds mates. And it forms a dative covalent bond with water. So what it does is it actually takes the H plus, it goes and sits with the H2O. Remember the H, the O, the H, the H plus went and sat at the pub over there. All right? Now, that was just a recap. So this guy here, this H plus needs to go and he attaches himself to an H3O plus like so. Okay? And the next bit is we end up with an OH minus over there. So we can see that that's the hydronium ion and that's the hydroxide ion. But this is not balanced. We actually need two of those to balance it, don't we? So now it's balanced, okay, there we go, we've got, he's gone there, okay, let's see, we've got 4, 3, 4, 2 oxygens, we are balanced. Now let us say that we've got a beaker of water standing over here, inside there are those two ions existing, which means that thus it's an equilibrium equation. I can write the expression of mass action. I say, all right, Kc is going to be the concentration of the H3O plus multiplied by the concentration of the OH minus divided by, theoretically, the concentration of the H2O, which is a liquid, hint, squared. But this is a liquid, therefore 1. Which means essentially it becomes the concentration of H3O plus multiplied by the concentration of OH minus. And we call that Kw, W standing for water. So water, I suppose stretching it to say it's dissolved in itself, it's ionized in itself. It naturally contains an element of H3O and OH minus. Well, hang on, remember when you must have heard the pH of water is 7? Actually, yes, we're going to see it in acids and bases. Water contains an equal amount of hydronium ion and hydroxyl ion. So they cancel each other out. because what is the hydroxyl ion? The OH minus is in fact the base, and this is the acid, and they are equal in water to give us a pH of 7. You're going to see this soon. Now over here, thus, we've got the dissociation constant of water. This number is equal to 1 times 10 to the minus 14. Let me rewrite that nice and clearly. Times 10 to the minus 14. Right? We're going to see this when we do pH calculations. Right? The acids and the bases, they dissociate equally. Therefore, that number technically we're going to have a look at in more detail. The next one we're going to look at, right, is this term solubility. Essentially, we're looking at how much of something dissolves in a, let's say, solvent, shall we? How much of something dissolves in a solvent? For the time being, I'm going to use the solvent is equal to water. Okay? Obviously, you can dissolve things in benzene, you can dissolve things in alcohol, you can dissolve them in carbon tetrachloride, blah-de-blah-de-blah, okay? In ether. Now, over here, we're just going to use water for the time being. Let us, before we start it, let's just consider what we're talking about here. This little investment of your time is well worth it before you get to the nitty-gritty. Because when you get to the nitty-gritty of solubility products, you're going to find that you're going to be asked to find, will something precipitate out or won't it? What do? We say we have got here a solvent is our liquid. If I now put a pile of salt in there, that is NaCl. You know that salt dissolves in water. What happens is the salt becomes Na plus and Cl minus, doesn't it? So up to a point, you will find it dissolve, but then it stops dissolving, does it not? When it's reached that point, what is it actually in? It's in equilibrium. So what we're saying is that the reaction is NaCl solid, okay? If you like plus water, but we can omit it in this case, goes to Na plus plus a Cl minus. I've only written the ionic equation. Thus, when I dissolve it, I get ions. So at equilibrium, what has happened? At equilibrium, each time one goes off to form an Na plus and a Cl minus, another one forms NaCl. At that point, no more salt can dissolve. No more substance can dissolve. It's the same concept. And it's you've got to be very careful with this. In our minds, we're saying we've got the salt, it's dissolved. We're not going to heat this at the moment. We just leave it. So there comes a point it's dissolved. How many of you have made a cup of tea, hot chocolate, cocoa, coffee, whatever, and for those of you who put 3 or 4 teaspoons of sugar into it, not a great thing to do, by the way, but I'm not going to do the whole health kick. Somebody else will surely take that up. But what it is that you will find, you see that sludge at the bottom, the undissolved sugar. It means that you could keep putting sugar in now, but no more is going to dissolve. All you're going to do is you're going to pile sugar into it. The same thing applies to my little heap of salt over there. It has reached maximum concentration. So therefore, we can say that we've got maximum concentration. So these guys are at a maximum. Therefore, if I write the expression K, it's equilibrium, concentration of Na plus times concentration of Cl minus divided by NaCl. Okay, hopefully you're all saying to me, that's a solid, Kevin. Yes, it is. It's 1, which gives us the concentration of Na plus times the concentration of Cl minus. That's an equilibrium expression, because at that particular temperature, no more can dissolve. Thus, we call this KSP. SP is the solubility product. Solubility product. At that point, no more can dissolve. That is critical, because let's just take a look at this in a little more detail, shall we? We say, all right. Well, let's take salt. Just let's stick with salt for a while. As you know, the KSP is equal to product over reactant. But this is equal to 1 in a KSP. So it's going to be the concentration of the two ions, isn't it, that we get. So if we have got magnesium hydroxide. Now remember, there's a 2 because that's a plus 2. 2 times minus 1 is minus 2, net 0 charge. Okay, and we put that in water. I'm just writing the ionic equation now. That is going to go to Mg plus 2 plus 2OH minus, is it not? We say, okay, whenever we've got an equation, we write 1 goes to 1 plus 2. Which means, if I write the expression of mass action for this character, what are we going to get? We're going to get KSP, because this is a solid. This here is aqueous, and that is aqueous. The aqueous means it's an ion in water. Aqueous means ion in water, right? KSP, the solubility product of this, is going to be equal to the concentration of the Mg plus 2 ions multiplied by the OH minus to the power of 2. Right. Now, in these cases here, we're going to have situations where we've got a power of 2. That is critical for solving the problems themselves. The other element of thinking of KSP, right? KSP is equal to, let us just say it's essentially I'm just going to use 2 ions here. This is the product, is it not? Okay, this is the product. Okay, therefore that is why it's called the solubility product. These are the 2 products, and it's the product of those I'm multiplying, so the product of the product, not go there. Now, therefore, once again, if KSP, it's doing its auto, KSP is, if KSP is large number, right, it means we get lots of products. Lots of products means lots of ions in the water, which means little reactant left, which means it's highly soluble, doesn't it? Because it's used up as many as possible of it. It's highly soluble. Well, obviously, the concomitant one to that is going to be, well, if KSP is a small number, it means little product. Means not many ions in solution. right? It means, therefore, lots of reactant left, which means it's relatively, and we call it insoluble. Thus, you can say soluble KSP high, insoluble KSP low. That's how it works. Therefore, the higher the KSP, the more soluble something is in water or a solvent. Okay? There are questions out there, but in essence, the principle says if it's actually a liquid, we are going to use the 1 for it, or a solid. Solubility product, generally we're going from a solid. Okay. Now, when we're going to, what I'm going to do is I'm going to keep this one short, and I'm going to then, on the next section, I'm going to go into more of the detail. So I'll rather have a short one for this. We've done the things, but now the question is, we're going to move on and we're going to start answering questions about what happens at the equilibrium point and how do we actually use this value of K, the Kc, Ka, Ksp, Kw. We're going to be focusing on Kc in the next ones. And I'm going to obviously do a Ksp. Acids and bases, we come back to this. We use Kw for that. Okay. So let's call that one quits. The next one we're going to do is we're going to look at some examples. I'll see you in the next one. Cheers. Bye.